The story of the universe's death did not begin with telescopes aimed at the heavens. It began in the dim light of laboratories, in the quiet scratching of chalk against slate. In the mid-19th century, long before the cosmos revealed its age or size, men of science were wrestling with an invisible law. The law of heat. Rudolf Clausius, a German physicist, noticed that heat never flowed backwards. A warmer body could give its energy to a cooler one, but the reverse never occurred. In 1865, he gave this imbalance a name, entropy. It was not simply a measurement of disorder, it was a prophecy of direction. With each transfer of energy, Clausius realized the universe itself was slipping, step by step, toward equilibrium. A final state in which no gradients remained and no further work could be done. William Thomson, known to history as Lord Kelvin, extended the thought to its chilling conclusion. If entropy must increase, then the cosmos itself must one day fall silent. No engine, no flame, no star could resist the pull of this thermodynamic current. Kelvin described it as a universal heat death, a moment when the universe would be uniform, motionless, and cold. The idea was so stark, so unsettling, that many dismissed it. Yet the mathematics was sound. Then came Ludwig Boltzmann, an Austrian genius who dared to connect the microscopic and the cosmic. He argued that entropy was the statistical tendency of atoms and molecules to drift toward states of higher probability. A room with evenly spread air was simply more likely than a room with all its molecules trapped in one corner. The universe, Boltzmann claimed, was no different. Over unimaginable spans of time, it too would collapse into the most probable condition. A sea of maximum entropy, devoid of usable energy. His vision was revolutionary and tragic. Boltzmann's contemporaries ridiculed the idea of a dying universe, a cosmos without purpose. His refusal to bend to the ridicule weighed heavily on him. In 1906, he ended his own life, leaving behind equations that would outlive his despair. Today, they remain etched into the foundation of physics, the mathematics of entropy carved into the future of the cosmos. And yet, for all their prescience, Clausius, Kelvin, and Boltzmann were still bound by the Newtonian dream of an eternal, clockwork universe. They had not yet glimpsed the deeper truth, that space and time themselves were malleable. In 1915, Albert Einstein shattered the illusion of a static cosmos. With his general theory of relativity, spacetime became a living fabric, curving under the weight of matter and energy. No longer was the universe a rigid stage. It was a participant in the drama. Galaxies could move apart, the fabric could stretch, the stage itself could evolve. Suddenly, entropy was not merely the fate of local systems. It was the destiny of the entire expanding universe. Still, Einstein himself resisted. He added a cosmological constant to his equations to prevent collapse or expansion, holding to the comforting notion of a static eternity. But in 1929, Edwin Hubble's careful measurements revealed that galaxies were retreating from one another. The universe was expanding, its future unsealed. Einstein would later call his constant the greatest blunder of my life. Though today, physicists see a faint outline of what we now call dark energy. The picture sharpened in 1965, when two engineers at Bell Labs, Arno Penzias and Robert Wilson, stumbled upon a faint hiss of microwaves that seemed to come from every direction in the sky. At first, they suspected pigeons nesting in their antenna. But when the noise persisted, the truth emerged. They had discovered the fossil glow of the Big Bang itself. This cosmic microwave background was the oldest light in existence. Photons released when the universe was only 380,000 years old. Unlike the fleeting radiance of stars, these photons had survived the entire sweep of cosmic history, stretched by expansion into invisible microwaves. They whispered of a universe once hot and dense, now cooling and fading. For the first time, humanity had a window not only into the birth of light, but into its inevitable death, from Clausius's first definition of entropy to Einstein's evolving cosmos. And from Boltzmann's equations to the faint relic glow of the microwave background, a timeline was forged. It told a story not of eternal cycles, but of an arrow. A one-way journey from blazing creation toward silence. It is this story, built on the minds of scientists who stared into the abyss of time. That leads us to the central question. If the universe began in fire and will end in cold, what lies in the shadows between the first photon and the last? For centuries, the night sky had offered a quiet illusion. Stars appeared eternal, their light unchanging, their patterns fixed. Even when telescopes revealed vast nebulae and countless galaxies, the human mind clung to permanence. The heavens seemed infinite in both space and time. But entropy, once applied beyond the walls of a laboratory, shattered that illusion. The shock was simple, yet devastating. The universe is not everlasting. It is dying. Entropy was not just a rule for engines or furnaces, it was a sentence written into the fabric of existence. Stars could not burn forever. Their fuel would one day be consumed. Even the grandest galaxies, bound together by gravity, would see their brilliance fade. The laws of thermodynamics pointed to an unavoidable conclusion. Every process that generates order also surrenders to disorder. Over eons, usable energy drains away until nothing remains but equilibrium, a uniform, lightless calm. The idea was unsettling enough in the 19th century. But the 20th century brought revelations that made the prospect even more terrifying when Edwin Hubble measured the faint stretching of light from distant galaxies in 1929. It covered a universe expanding in every direction. This was no static stage. Space itself was swelling, carrying galaxies apart, thinning the light between them. The implication was unavoidable. If the universe is expanding now, then in the past it must have been smaller, hotter, and denser. The eternal cosmos collapsed into a finite history, a beginning. And if there was a beginning, there must also be an end. The shock grew sharper still with the work of Stephen Hawking and Jacob Bekenstein in the 1970s. Black holes, once thought to be eternal prisons of gravity, were revealed to be mortal. Hawking showed that the fabric of quantum fields around a black hole's horizon would paradoxically cause it to evaporate. The giants of the cosmos would eventually shrink, flicker, and vanish into faint radiation. Even the most powerful engines of destruction could not escape entropy's reach. What this meant was staggering. Not only would stars die, not only would galaxies dim, even black holes, the supposed graveyards of matter, would themselves become ghosts, their mass bleeding away into nothingness across unimaginable timescales. Physicists began to trace the chronology of this death. In tens of billions of years, the last brilliant stars would burn out, leaving behind the husks of white dwarfs, neutron stars, and black holes. In quadrillions of years, those remnants would fade, collide, or decay. In 10,100 years, the last. Black holes would vanish in whispers of hawkingradiation, scattering their final photons into the dark. The sheer immensity of the numbers defied human comprehension, but perhaps the greatest shock was not in the length of the story, but in its certainty. The universe was not trending toward greater complexity or toward eternal cycles. Its arrow pointed one way, toward equilibrium, silence, and darkness. Entropy became the ultimate contradiction to human instinct. On Earth, life seemed to build. Order from chaos, forests grow, minds imagine, civilizations rise. But these small local triumphs are illusions borrowed from the universe's greater descent. Every flame of life, every burst of creation, is bought with a greater release of energy, a greater rise in entropy. Even life itself is not exempt. It is simply a brief rebellion against the cold inevitability of thermodynamics. By the mid-20th century, a darker truth compounded the dread. The discovery of cosmic acceleration in the late 1990s, through distant supernova surveys, revealed that the universe is not merely expanding, it is accelerating. Some hidden force, named darkenergy, is pushing galaxies apart faster and faster. If this continues, the cosmos will not only cool, it will become unreachable. One by one, galaxies will slip beyond the cosmic horizon, carried away at speeds exceeding that of light by the swelling of space itself. Their stars, their light, their histories will vanish from view. To any observer in the far future, the universe will seem lonely, barren, and empty. A single island of darkness floating in an immeasurable void. The scientific world reeled. The laws of entropy married to cosmic expansion painted a destiny more unsettling than any myth. The heavens would not collapse in fire or be reborn in cycles. They would fade in silence, and the silence would last forever. The human imagination struggled against it. Poets had once spoken of the stars as eternal witnesses, gods written in fire. Philosophers had described an infinite cosmos with no beginning and no end. Now, physicists whispered of a heat death, a universe where no witness remains, no memory lingers, no flame burns. The shock grew sharper still with the work of Stephen Hawking and Jacob Bekenstein in the 1970s. Black holes, once thought to be eternal prisons of gravity, were revealed to be mortal. Hawking showed that the fabric of quantum fields around a black hole's horizon would paradoxically cause it to evaporate. The giants of the cosmos would eventually shrink, flicker, and vanish into faint radiation. Even the most powerful engines of destruction could not escape entropy's reach. What this meant was staggering. Not only would stars die, not only would galaxies dim, even black holes, the supposed graveyards of matter, would themselves become ghosts, their mass bleeding away into nothingness across unimaginable timescales. Physicists began to trace the chronology of this death. In tens of billions of years, the last brilliant stars would burn out, leaving behind the husks of white dwarfs, neutron stars, and black holes. In quadrillions of years, those remnants would fade, collide, or decay. In 10,100 years, the last. Black holes would vanish in whispers of hawkingradiation, scattering their final photons into the dark. The sheer immensity of the numbers defied human comprehension, but perhaps the greatest shock was not in the length of the story, but in its certainty. The universe was not trending toward greater complexity or toward eternal cycles. Its arrow pointed one way, toward equilibrium, silence, and darkness. Entropy became the ultimate contradiction to human instinct. On Earth, life seemed to build. Order from chaos. Forests grow. Minds imagine. Civilizations rise. But these small local triumphs are illusions borrowed from the universe's greater descent. Every flame of life, every burst of creation, is bought with a greater release of energy, a greater rise in entropy. Even life itself is not exempt. It is simply a brief rebellion against the cold inevitability of thermodynamics. By the mid-20th century, a darker truth compounded the dread. The discovery of cosmic acceleration in the late 1990s, through distant supernova surveys, revealed that the universe is not merely expanding, it is accelerating. Some hidden force, named darkenergy, is pushing galaxies apart faster and faster. If this continues, the cosmos will not only cool, it will become unreachable. One by one, galaxies will slip beyond the cosmic horizon, carried away at speeds exceeding that of light by the swelling of space itself. Their stars, their light, their histories will vanish from view. To any observer in the far future, the universe will seem lonely, barren, and empty. A single island of darkness floating in an immeasurable void. The scientific world reeled. Laws of entropy, married to cosmic expansion, painted a destiny more unsettling than any myth. The heavens would not collapse in fire or be reborn in cycles. They would fade in silence, and the silence would last forever. The human imagination struggled against it. Poets had once spoken of the stars as eternal witnesses, gods written in fire. Philosophers had described an infinite cosmos with no beginning and no end. Now, physicists whispered of a heat death, a universe where no witness remains, no memory lingers, no flame burns. The terror lay not in violence, but in stillness. Not in a cataclysm, but in the slow surrender of time itself. This was the shock, that the universe for all its grandeur, is not built to endure. Its fate is not to blaze in glory, but to dissolve into uniformity. And in that uniformity, time itself may lose meaning. When nothing changes, when no event can mark the difference between before and after, the concept of time may cease to exist. The cosmic narrative that had begun in fire, the Big Bang, the birth of stars, the rise of galaxies, the spark of consciousness, would end not with an explosion, but with a whisper of the last photon, fading into the endless dark. And so, the question loomed heavier than ever. If this is the fate that awaits, what is left for science to uncover? What deeper mysteries lie hidden in the data, in the relic light, in the strange acceleration of expansion? The universe had revealed its mortality, but the full scope of its dying remained veiled. The death of the universe is not written in sudden catastrophe. It is written silence in a slow unraveling across unimaginable spans of time. Once scientists accepted entropy's dominion, the next question emerged. How would the great unraveling actually unfold? What shape would the darkness take? The investigation began with the fate of stars. Every star is a fragile balance between gravity and fusion. In its core, nuclear reactions force hydrogen atoms together, releasing the radiant light that streams across the cosmos. But fuel is finite. When the hydrogen is gone, stars transform. Some swell into red giants, casting off their outer layers, leaving behind the dim cinders of white dwarfs. Others collapse in violence, producing neutron stars or black holes. Astronomers traced the lifetimes of stars across billions of years. Large stars would perish quickly, their brilliance gone in only millions of years. Smaller stars, red dwarfs, burning faintly but steadily, might endure for trillions. But even they cannot escape entropy. Eventually, every star, no matter its size, must consume its last reserves. The universe, scientists realized, will move into a twilight called the stelliferous era, the age of stars. Today, we still live in this era, surrounded by galaxies ablaze with light. Yet in the far future, one by one, the stars will wink out. The cosmos will dim, leaving behind only remnants, black dwarfs, neutron stars, and black holes scattered through expanding space. Physicists extended their vision beyond this twilight into epochs so distant that language itself struggles to hold the numbers. After 1,015 years, a million billion years, the last faint red dwarfs will extinguish. No new stars will be born. Darkness will take hold. The relics left behind will enter the degenerate era. White dwarfs, once the cores of stars, will cool into black dwarfs, frozen spheres of carbon and oxygen, radiating no heat, shining no light. Neutron stars, too, will fade, their magnetic fields and residual warmth leaking into the void. The universe will be populated only by the corpses of stars drifting silently through the dark. But entropy does not stop with stillness. Gravity continues its quiet work. Over time, remnants may collide, creating bursts of energy and an otherwise silent cosmos. Black holes, formed from collapsed stars or galactic cores, will swallow matter and light. Growing fatter in the darkness, then comes the revelation of hawkingradiation. Even black holes, the great prisons of the universe, cannot endure forever. Quantum mechanics dictates that pairs of virtual particles flicker into existence near an event horizon. Occasionally, one falls in while the other escapes, stealing a fraction of the black hole's mass. Across vast ages, this leakage becomes absolute. A black hole the size of a star may take 1,067 years to evaporate. The titanic monsters at galactic centers may endure far longer, perhaps 10,100 years, before vanishing into nothing. This is the black hole era, a cosmos populated by evaporating giants, whispering their energy away into the void. The light they release will be faint, stretched by expansion, diluted into invisibility. Yet these photons mark the last flickers of structure in the universe. After their passing comes the final act. The dark era. Matter itself may not survive. Protons, the building blocks of atoms, could decay into lighter particles, though this remains uncertain. If proton decay is real, then even the remnants of stars will crumble into radiation. If not, then black dwarfs and neutron stars may persist. But they will be cold, inert, and eternally silent. Scientists piece together this cosmic sequence with telescopes, particle accelerators, and theory. They mapped stellar lifetimes, studied nuclear fusion, and measured cosmic expansion. Each new discovery tightened the script of the universe's demise. And yet, the deeper they looked, the more disturbing the mystery became. Entropy, not only described the end of stars, but the fading of light itself. Photons, the very carriers of existence's story, would stretch endlessly as space expanded. Their wavelengths would grow so long that they could no longer interact with matter, drifting uselessly through the void. Eventually, each photon would carry so little energy that it would be indistinguishable from nothing at all. Here lay the chilling realization. The last photon of the cosmos will not vanish in a blaze, but in a slow fading, its identity stretched, until it dissolves into silence. The investigation revealed not only the physics of death, but the timescales of oblivion. Numbers rose to powers beyond imagination. 1,015 years. YY years. 10,000. 100 years. In these spans, every familiar anchor of meaning disappeared. Stars, galaxies, black holes, even matter itself. What remained was a universe still expanding, still governed by entropy, but emptied of everything that once gave it texture. And in this emptiness, new questions were born. Would the universe truly stop at equilibrium? Or could quantum fluctuations spark new beginnings? Could entropy's march give rise by pure chance to the fleeting illusion of order again? Perhaps. Even the strange thought experiments called Boltzmann brains, minds emerging for an instant in the dark. The deeper scientists probed, the clearer the paradox became. The cosmos seemed destined for silence, yet its very laws allowed for fleeting sparks. Improbable but possible, the investigation had revealed the framework of the end. But the story was far from finished, for as telescopes scanned the heavens, they discovered that the darkness was not merely coming, it was accelerating. Something deeper, stranger, was driving the universe apart, rushing it more swiftly toward oblivion. The mystery did not close. It widened at first. Entropy seemed a patient executioner. Stars would burn for trillions of years, black holes for eons longer still. The death of the cosmos appeared to be a slow descent, stretched across unimaginable scales of time. But in the late 20th century, the universe revealed a darker secret. The descent was not slow. It was accelerating in 1998, astronomers measuring. Distant type Ia supernova, stellar explosions that serve as cosmic mile markers, made an astonishing discovery. The light from these explosions was dimmer than expected. Galaxies were not just drifting apart. They were speeding away faster and faster. Something unseen, some repulsive force, was driving the universe outward with increasing urgency. This invisible agent was given a name, darkenergy. It was unlike anything in the known catalog of physics. Not matter, not radiation, but an energy woven into the fabric of space itself. Its presence was overwhelming. Today, observations suggest that dark energy accounts for nearly 70% of the cosmos. The visible stars, planets, and galaxies, the entirety of familiar existence, make up less than 5. For the fate of the universe, the implications were catastrophic. If dark energy remains constant, galaxies will race farther apart. Their light redshifted until it vanishes beyond detectability. Future observers, billions of years from now, will see only their own galaxy adrift in silence, unaware that a cosmos once blazed around them. But if dark energy is not constant, if its strength grows with time, the picture grows even more disturbing. Some models suggest a scenario called the bigrip. In this vision of the future, dark energy's repulsion becomes so violent that it overwhelms all other forces. First, galaxies are torn from one another. Then, stars are ripped from galaxies. Eventually, gravity itself cannot bind solar systems or even planets. In the final instance, atoms are pulled apart, the fabric of matter itself shredded by expansion. The universe does not fade quietly into entropy. It disintegrates in a crescendo of destruction. Even without the big rip, the acceleration deepens. The horror of entropy. For as galaxies flee beyond the cosmic horizon, their light becomes forever unreachable. Information itself, the history of stars, the memory of galaxies, is erased. The universe does not merely cool. It forgets. Physicists began to wrestle with an unsettling paradox. Entropy predicts equilibrium, a calm in which all states are equal. But cosmic acceleration suggests a more absolute silence, a silence in which even equilibrium cannot be shared because the pieces of the cosmos are torn infinitely apart. Does this mean that entropy's final state is not uniformity, but isolation? Does darkness deepen into something beyond heat death, a scattering of nothing across nothing? The mystery was sharpened further by quantum theory. According to some calculations, the universe may exist in what is called a false vacuum, a metastable state that only appears stable. If so, then at any moment, a quantum fluctuation could trigger vacuum decay, a bubble of lower energy reality, expanding at the speed of light. Inside this bubble, the laws of physics themselves would be rewritten, obliterating everything in its path. Unlike heat death, vacuum decay would not wait for 10,100 years. It could begin tomorrow without warning, rewriting the destiny of all existence in an instant. What began as the simple story of entropy had escalated into something far stranger. The universe was not merely dying of cold. It was being accelerated toward silence by a force no one understood. It was balanced on the edge of instability, its very fabric vulnerable to collapse. And still, another paradox loomed. In a universe governed by expansion and decay, is true nothingness ever possible? Some physicists argue that quantum fields never vanish, that fluctuations persist even in empty space. If so, then the death of the universe may not be an end, but a stage. In infinite time, random fluctuations might assemble fleeting islands of order, temporary structures, bursts of light, perhaps even minds. These are the so-called Boltzmann brains, consciousnesses born not from evolution, but from randomness, flickering into awareness before dissolving again into the void. The thought is unsettling, almost nightmarish. In an eternity of darkness, could such phantom observers outnumber all the beings who ever lived in the bright age of stars? If so, what does it mean to exist now in what seems like a coherent universe? Could reality itself be a fluctuation? The mystery deepens not only in theory, but in scale. The timescales required to describe these possibilities dwarf imagination. 1,020 years for stellar remnants to fade. 10,100 years for black holes to evaporate. 10,120 years for the last faint traces of radiation to stretch beyond measure. Human numbers, human language, even human thought strains to hold them. In confronting these magnitudes, we confront the limits of our own existence, brief sparks, measured in decades, against the abyss of eternity. And so, the investigation that began with entropy and stellar death has spiraled into questions that reach the edge of physics and philosophy alike. The death of the universe is not simply a matter of cooling stars. It is a puzzle of expansion, of quantum instability, of fluctuations that hint at new beginnings hidden within endings. The cosmos does not merely decline. It accelerates into darkness. It threatens to rip itself apart. It may even betray the laws we believe govern it, collapsing into something else entirely. The mystery, once thought to be the silent fate of entropy, has become far stranger, a death. That is not singular, but plural, branching into possibilities that both terrify and mesmerize. And in this growing labyrinth of endings, science turns to its only lantern, theory. If entropy sets the stage and dark energy hastens the act, then speculation offers the only glimpse of what lies beyond the curtain. the death of the universe is not a single path. It is a branching tree of possibilities, each rooted in physics, each reaching toward an end more unsettling than the last. Entropy is certain, but the manner of its dominion remains a subject of deep speculation. The most widely accepted vision is the heat death. In this scenario, expansion continues under the influence of dark energy, galaxies drift apart, stars burn out, and black holes evaporate. The cosmos slides toward maximum entropy, a final equilibrium where no gradients remain. No work can be done, and time itself loses meaning. It is the quietest ending, an infinite darkness, a silence that stretches forever. For many cosmologists, it is the natural consequence of thermodynamics applied to the whole. Yet not all scientists accept such some propose more violent possibilities. If dark energy's repulsion grows stronger over time, the universe could meet its end in a big rip. Here, acceleration does not stop at galaxies. It infiltrates clusters, star systems, planets, even atoms. Gravity, electromagnetism, and the nuclear forces would eventually fail to resist. The cosmos would not fade but tear itself apart, its very fabric shredded into nothingness. The timescale for such a catastrophe depends on the nature of dark energy, perhaps trillions of years away, perhaps closer than imagined. Others imagine the opposite, a collapse. If dark energy is not constant, but unstable, its pressure could one day reverse. Expansion would slow, then halt, then contract. Galaxies would converge, stars would collide, matter and radiation would compress until the universe imploded in a big crunch. Some theories stretch further. The collapse could trigger a new Big Bang, birthing a fresh cosmos and a cycle of death and rebirth. In this view, our universe is but one act in an eternal play, each cycle writing a new script of stars and galaxies upon the ashes of the last. Still more radical is the possibility of a multiverse. In the framework of eternal inflation, space is not uniform but endlessly budding. Our observable universe may be one bubble in an infinite foam. If so, then its death may not be final. Beyond our fading horizon, other universes may blaze with light, governed by different laws of physics. Some may collapse quickly, others may endure longer, others still may never cool. Heat death, big rip, or big crunch may be only local fates, irrelevant to the greater ocean of universes in which our bubble floats. But quantum theory introduces possibilities stranger still. The notion of a false vacuum suggests that our universe may rest in a metastable state, not the lowest possible energy, but a plateau waiting to collapse. If so, then at any moment, a quantum fluctuation could nucleate a bubble of true vacuum. This bubble would expand at the speed of light, erasing everything in its path. The constants of physics, the structure of matter, even the dimensions of space-time itself would be rewritten. For those within the bubble, no time would pass. The transition would be instantaneous. The universe, as it is known, would vanish without warning. And yet, against this landscape of endings, another question haunts cosmology. Can nothingness ever truly exist? Quantum fields suggest that emptiness is never absolute. Even in a vacuum, fluctuations seethe, birthing and annihilating particles in a restless foam. If heat death is the destination, then these fluctuations may persist even there, in the dark eternity after the last photon fades. Given infinite time, they could conjure momentary structures of startling complexity. This is the unsettling speculation of Boltzmann brains. In an infinite sea of random fluctuations, the appearance of isolated consciousnesses becomes inevitable. Minds that flicker into being fully formed, with false memories of a universe that no longer exists, they would emerge, contemplate the void, and dissolve again into nothing. The idea challenges not only physics, but philosophy. If such minds vastly outnumber evolved beings, what does it mean to be conscious now? Are we part of the ordered universe? Or are we ourselves illusions born of entropy's game? Each of these theories stretches the imagination to its limits. yet all remain tethered to real physics. The equations of relativity, the probabilities of quantum mechanics, the principles of thermodynamics, each offers a different doorway into the darkness. None provides certainty, but each reveals how fragile, how temporary, how strange our reality might be. Even Stephen Hawking allowed for speculation. He once suggested that the information swallowed by black holes might never truly be lost, but imprinted in subtle ways upon their evaporation. If true, then perhaps the universe itself preserves a trace of its story, even in death. Perhaps entropy does not erase memory completely, but transforms it into a language too faint, too diffuse, for us to yet decipher. Theories and speculations do more than map the end. They reflect the tension between two human impulses, the desire for permanence and the confrontation with impermanence. Heat death strips away all permanence, offering only an eternal silence. The Big Crunch, in contrast, promises cycles of renewal, echoes of hope, and endless repetition. The multiverse whispers that even if this cosmos dies, others may thrive. The false vacuum offers the stark reminder that existence is fragile, balanced. On a knife's edge, what unites them all is uncertainty. The fate of the universe remains veiled, suspended between models, awaiting the verdict of observation. Theories multiply because data is incomplete. The death of the universe cannot yet be measured directly. It can only be inferred from the faint patterns of galaxies, the whisper of ancient photons, and the strange pull of invisible energy. Speculation becomes the language of humility. To imagine the end is not only to calculate, but to wonder. And so, physics does not close the story here. It points instead toward the instruments that may one day choose between these visions, to the tools now aimed into the dark, searching for the final word on the fate of all things. If the fate of the universe is written in its laws, then humanity's only hope of glimpsing that future lies in the tools of science. The fragile machines built to catch whispers of light, trace the pull of gravity, and measure the faintest tremors in the fabric of spacetime. Theories may sketch the outlines of cosmic death, but only instruments can decide between them. The first and most ancient tool is light itself. Every photon carries information about its origin, the distance of galaxies, the temperature of space, the fingerprints of matter that once absorbed or emitted it. By mapping this light, astronomers attempt to chart not just the past, but the trajectory of the future. In the mid-20th century, radio antennas revealed the cosmic microwave background, the afterglow of the Big Bang. Since then, satellites such as COBE, WMAP, and the Planck Observatory have refined its portrait. These missions traced the temperature of the relic radiation to astonishing precision, revealing fluctuations of only 1 part in 100,000. From those tiny ripples came the seeds of galaxies. From their distribution came clues about the universe's density, its composition, and its expansion. Each refinement narrowed the possibilities of the cosmos' fate, yet the most urgent task remains the measurement of dark energy. If entropy is the law that ensures an end, dark energy is the accelerator that determines how quickly it comes. To study it, astronomers turn to Type Ia supernova, stellar detonations so luminous they can outshine entire galaxies. These explosions serve as standard candles, objects of predictable brightness that allow distances to be measured across billions of light years. The supernova surveys of the 1990s revealed that expansion was accelerating, and today, new observatories continue the task. The Dark Energy Survey, conducted from Chile, scanned the sky for 6 years, mapping hundreds of millions of galaxies. The Euclid mission, launched by the European Space Agency, now appears deeper still, measuring the subtle bending of light by cosmic structure. And the Vera C. Rubin Observatory, with its legacy survey of space and time, will soon watch the entire southern sky repeatedly, catching transient events and charting the large-scale structure of the universe. Together, they aim to answer the question, is dark energy constant, or is it changing? The difference may decide whether the universe ends in silence, in rupture or in rebirth. Meanwhile, particle physicists seek answers from the smallest scales. If protons decay, as some theories predict, then even the most inert remnants of stars will not endure. Experiments such as Super Kamiokande in Japan, a vast tank of water buried beneath a mountain, watch for the faint flashes of light that would betray proton decay. None have been seen, but the search continues. Because the fate of matter itself may hinge on this one answer. Elsewhere, the Large Hadron Collider probes the stability of the vacuum, smashing particles together to measure the Higgs field with exquisite precision. The results hint that our universe may indeed be metastable, balanced in a false vacuum that could one day collapse. If so, then entropy is not the only threat. Quantum fragility haunts existence from within, beyond light and particles. Another window has opened: gravitational waves. Detected for the first time in 2015, these ripples in spacetime carry information from events invisible in any telescope. As detectors such as LIGO, Virgo, and Cagra improve, they may reveal black hole mergers across the universe, mapping how these giants form, grow, and perhaps evaporate. Their fates, stretched into unimaginable timeframes, are critical to the story of cosmic death. And above them all, new eyes rise into space. The James Webb Space Telescope, launched in 2021, peers into the infrared, capturing the faintest galaxies at the edge of visibility. Its task is not only to see the first stars, but to measure how structure evolves under the pull of dark energy. The next generation of telescopes, the Nancy Grace Roman Space Telescope, the extremely large telescope and beyond, will push this precision further, tracing the expansion of the cosmos with clarity never before possible. Together, these instruments form a chorus, each tuned to a different note of the cosmic song. Some listen to the oldest photons. Some catch the faint flashes of dying stars. Some measure the smallest tremors of matter itself. All work together to decide which speculation becomes truth. Yet even as data sharpens, mystery persists. Dark energy remains a cipher, its origin unknown. Proton decay eludes detection. The Higgs field whispers of instability but refuses confirmation. Each new tool answers one question only to open three more. The fate of the universe, like the horizon of a black hole, retreats as we approach, and still, the effort continues. For to measure the cosmos is not only to predict its death, but to understand its life. Every refinement in cosmology reveals not just the end of time, but the improbable chance that stars, galaxies, and minds exist at all that science. Then becomes not just an act of measurement, but of defiance. With fragile instruments on a small planet, a species that will last for only a cosmic heartbeat dares to trace the story of trillions of years, to ask what comes after the last photon. The tools may never see the end they predict, but they carve meaning from its shadow. For in the end, every telescope, every detector, every collider is a mirror as much as it is a window. They reveal not only the cosmos, but the hunger of the human mind, to know, to measure, to imagine, to face entropy not with resignation, but with understanding. And with this understanding comes a final turn, one that moves beyond equations, and data beyond models and speculation, into the realm of reflection. For if the universe is destined for silence, what does that silence mean? What does the death of light reveal about the meaning of life, of thought, of existence itself?